You ever drive past one of those massive industrial plants, an oil refinery with all its crazy maze of pipes and towers, and just wonder, how does that whole thing not just go boom? Well, today we're going to pull back the curtain on the incredible, unseen engineering that keeps all of that power safely in check.
So, really, what is the one thing that stands between a smoothly running plant and a major catastrophe? It all boils down to a constant, invisible war against one thing: immense, incredible pressure.
I mean, think about it. Every single pipe, every vessel in there is like a balloon being pushed to its limits, holding back unbelievable forces. This isn't just a story about some pipes and valves. It's about foresight, it's about physics, and it's about the brilliant design of systems that are literally built to fail, safely.
Okay, to really get a handle on this, let's bring it way down to something we all know: a pressure cooker. You build up heat, the pressure inside starts to skyrocket, and if you don't have that little valve on top to let off steam, you've got a kitchen disaster on your hands. Now, just imagine that, but scaled up to the size of a city block. That's the challenge.
And what's wild is the sheer number of ways things can go wrong. I mean, look at this list, which comes from the industry playbook API 521. Engineers have to plan for every single one of these. A blocked pipe? Sure, that's kind of obvious. But what about a total plant-wide power outage that kills all the cooling systems? Or an external fire right next to a tank, just baking it from the outside? Each one of these is a totally unique problem that the safety system has to be ready to solve in an instant.
So when things start going sideways and that pressure needle starts climbing into the red zone, what's the very first line of defense? Well, it's the real unsung hero of process safety.
It's this thing, the pressure relief device, or PRD. This is exactly like that little rattling valve on your pressure cooker. What's so amazing about it is that it's completely mechanical. There are no computers, no electricity, no buttons to push. It just sits there, and when the pressure inside hits one very specific, carefully calculated number, pop, it opens. Its only job in the entire world is to open up and prevent that piece of equipment from turning into shrapnel. Okay, but that leads to the next big question, right? The valve opens, and this super high-pressure, potentially flammable stuff comes screaming out. You can't just, vent that into the atmosphere right where people are working. So where in the world does it all go? Well, it gets onto what you can think of as a safety superhighway. That PRD, that valve, it's really just the on-ramp. It leads to a whole other, much bigger network of pipes and equipment that's designed for one purpose: to handle that sudden, violent, chaotic release of energy. So let's follow the flow, shall we? The PRD opens with a roar, and this fluid, which is usually a messy mix of both liquid and vapor, it just blasts into a huge collection pipe. They call it a header. And this header channels everything toward the next and, maybe most important, stop on the journey. And that stop is the knockout drum. Because here's the thing. You absolutely, under no circumstances, can send a big slug of flammable liquid up to a lit flare. That is how you get something they call a rain of fire, which is exactly as terrifying as it sounds. So the knockout drum is basically a giant tank that lets the whole stream slow down, and the heavy liquid knocks out of the flow and falls to the bottom. Only the clean vapor gets to continue on its way. And this really shows you none of this is guesswork. I mean, look at this chart. To figure out the exact right size for every piece of this system, engineers use incredibly complex charts like this one from API 521. It helps them predict precisely how a liquid will behave when it flashes, when it explodes from a high-pressure liquid into a low-pressure gas. Getting that math right is what makes sure the whole safety highway doesn't get overwhelmed. All right, this journey brings us to the final stop, and it's the most visible part of the whole system. It's the one thing you can probably see from miles away: the flare stack. Now, a lot of people see a flare and they think, oh, they're just burning off waste. But that's not its main job. First and foremost, a flare is a safety device. It's a highly engineered combustion machine that takes those dangerous vapors we just separated and safely burns them, converting them into much less harmful things like CO2 and water. It's the last, safest way to dispose of that energy. And the amount of energy we're talking about is just staggering. To put it in perspective, the standard specifies the absolute maximum thermal radiation, that's heat, that a person can be exposed to. And that number is 6.31 kilowatts per square meter. That single number dictates how tall the flare has to be and how big the keep-out zone around it is, all to protect people from a blast of invisible heat. So let's just zoom out for a second.
We've seen all the hardware, right? The valves, the drums, the flares. But what's the thinking behind it all? What's the guiding philosophy that helps engineers decide what to plan for?
It really all comes down to a core idea in engineering called single jeopardy. Basically, the rule is you have to design a system that can handle any one thing going wrong at a time. So your system has to be able to handle a total power failure or an external fire. What it's not required to handle is a total power failure and an external fire happening at the exact same time, because the odds of two completely unrelated disasters happening at once are just astronomically low. It's a way of being safe and practical at the same time.
And this isn't just a friendly suggestion. This philosophy is written into law, basically. Look at this quote from the Standard. It doesn't say the designer should do this or might want to do this. It says the designer shall. And in the world of engineering, shall is a command. It's an absolute, non-negotiable, you must do this requirement.
And I think the biggest thing to take away from all this is that the PRD and the flare are not working alone. They're actually the last line of defense in a deep, multi-layered strategy. Think about it. Long before that valve ever opens, the plant's normal control system is trying to fix the problem. If that doesn't work, alarms start blaring for an operator to step in. If that doesn't work, an automated shutdown system might kick in. That pressure relief device is truly the final, purely mechanical backstop when everything else has failed. So, the next time you see one of those industrial giants, remember this. Its safety is not an accident. It's not luck. It is the hard-won result of decades of learning from past mistakes, thousands of pages of engineering standards, and just layer after layer of brilliant, meticulous, and mostly invisible design. These systems really are the silent guardians of our modern world. And it kind of makes you wonder, doesn't it? What other hidden safety systems built on these exact same principles are working all around us every single day to keep us safe?